Alrighty, in part 5 here, we are going to finish our elimination reactions, okay, by getting the E1 mechanism, see a little bit about stereochemistry of elimination reactions, and that'll leave part 6 and 7, where we look at competition between substitution and elimination. Okay? But our last reaction class is E1 reactions, okay, elimination unimolecular. So just like the substitution, where we saw unimolecular, this is going to go through a carbocation intermediate. And the good news there is that you really only have to worry about these for tertiary alkyl halides, right? Because only the alkyl halide is involved in the rate determining step, right? The slow step there, as we can see from the rate law. And we know, right, if you're thinking about relating it to a substitution reaction, that it's got to go through a carbocation, and tertiary carbocations are most stable. So what's the mechanism look like? The alkyl halide, right, breaks the bond, so your leaving group departs, forms your carbocation intermediate, okay? Then a base comes in, plucks off a proton from one of your beta carbons, that electron density shifts over, forms your pi bond in your product. Okay. And of course, the first step, the formation of the carbocation, is the slow step. But the big question here is, how the heck are we deprotonating an sp3 carbon over here with a pKa of 60, give or take, with a weak base, right? How is all this going on? How is this bond just breaking? Right? So what's the reason for this mechanism? It's coming up on these next slides. Well, the first thing, how is the weak base removing a proton from an sp3 carbon? Okay. Well, it's that idea of hyperconjugation that we've continued to see throughout the course of organic, right? Hyperconjugation, when you've got sigma bond electrons that are spreading out into an empty p orbital. Okay. So the presence, even though this beta carbon here is sp3 hybridized, right? The presence of the positive charge on the carbocation greatly reduces the pKa of that acidic hydrogen, right? Because electron density has shifted over into the vacant p orbital, which has weakened the carbon-hydrogen bond, right? Less electron density here between the two means it's a weaker bond, meaning it's a lower pKa and it's more acidic. So that's why we're able to deprotonate that thing. And we also have to keep in mind, right, that E1 reactions, just like E2 reactions, are regioselective, the major product being the more stable alkene in both situations. We're still following Zaytev's rule. We're just getting there by a different mechanism. Okay. So now, right, looking at the more stable alkene being our major product, right, it's lower in energy, both in the final product and in the transition state. And these are more stable products overall, which is what's allowing us to drive this reaction forward, it being exergonic, okay, which is why the reaction proceeds. And same rules as E2 reactions and substitutions. Okay, the most reactive alkyl halides will be alkyl iodides, okay, because that's the best leaving group. Weakest base is the best leaving group, so iodide's the best, followed by bromide, chloride, and fluoride. We talked about just in the last video how fluoride is a bad leaving group. Okay. So most of the rules are the same, right? But what we need to keep in mind is the type of elimination that an alkyl halide is going to undergo. Now, only tertiary alkyl halides are going to undergo E1 reactions, as I mentioned in the beginning, because they can form a tertiary carbocation, which is stable enough to form, right? We're not going to do that with a primary or a secondary alkyl halide. We're not going to form a primary or a secondary carbocation. Those are only going to undergo E2 reactions. It's also because these reactions have high concentrations of base, typically being the solvent, that increases the propensity for an E2 reaction, okay, that high concentration. But there is a bit of an issue, right? If something's tertiary, it could do E1 or it could do E2, right? So that's the challenge, because the bonds broken and the bonds formed are the same at the end of the day. Just the way it happens, the mechanism is different. Okay. So this is a good slide to have committed, right? Tertiary alkyl halides, as we just said, can do both E1 and E2. If it's primary or secondary, it's only going to do E2. Right? So now, if it's tertiary, right, and don't worry about the rate law derivations that are going on in the textbook, right? You can determine this information experimentally. Right? But the big takeaway right now is if something is tertiary and it has a strong base at high concentration, it's going to favor E2. Okay. If you're using a weak base, then it's going to favor E1. Okay. Specifically at lower concentrations too. Okay. So high concentration and strong base, those favor E2. Low concentration, weak base, favor E1. So make sure you take that into mind, right? We talked about base strength previously. Something that's negatively charged, for example, is going to be a stronger base, favor E2. Right? Take that all in mind. The factors for a tertiary alkyl halide, is it going to be E2 or is it going to be E1? And know the mechanism for both. Okay. But if it's primary or secondary, it's only going to do an E2 if it's an elimination. Okay. So as I mentioned, right, we're going to talk about stereoselectivity too. We talked about the regiochemistry and Zev's rule, which we'll always follow unless we've got fluoride as a leaving group or we've got delocalized electrons. But what about the stereochemistry? Okay. Now, in elimination, in E2 specifically, okay, our sp3 hybridized orbitals have to be parallel to one another due to the pi bond that ends up getting formed. Okay, in order to get the maximum overlap in that pi bond, the sp3 orbitals have to be parallel to one another. Okay? And that can only happen in one way. Okay, they're parallel and they're on exact opposite sides of one another. Okay? That's called an anti-elimination, or they're parallel to one another and they're on the same side. And that's called a syn elimination. Okay? So these look kind of like a Newman projection. These are actually called sawhorse projections to show how these are parallel to one another. Okay, so anti or syn. Okay. Now, again, they have to be parallel to get that overlap in the orbital. Okay. Now, the anti-elimination, where they're on opposite sides over here, is when it's a staggered conformation, thinking back to your Newman projections. Okay. Now, a syn elimination over here is when they are in the eclipsed conformation. Now, we know from our Newman projections that this is more stable to begin with, that more stable conformation here. It also here is extra stable, keeping in mind the fact that a leaving group is electron rich, thinking about our halides, for example, and your base is electron rich. So those are going to repel one another because of the like charges. Yep. So that is going to affect our stereochem, right? An alkene that can be formed can also be E or Z. Okay? E is preferred considering our beta carbon that has multiple hydrogens or multiple beta carbons, right? The E is preferred because, as we've learned before, an E alkene is more stable because it takes those bulky groups, right, and puts them on opposite sides of one another. Here they're closer together, hence why Z is the minor product. Okay. So E is preferred because it's more stable to begin with, right? And E is also preferred because it can be formed from that anti-elimination, right? Two possible conformers where the hydrogen and the bromine are in an anti-configuration here and here, but we're going to form the more stable conformer overall, right? Hence why E following Zaytev's rule. Don't forget about that, right? That's the first thing to determine your beta carbon. And then E specifically will be the major group, the major product. And the larger the group, the greater the degree of selectivity. Right? If I crank that up to a T-butyl group versus just a methyl or an ethyl, for example, then that's going to be an even larger degree of major product. Okay. Again, this is looking at E2 reactions. Okay. But what about if there's only one hydrogen on your beta carbon to use? Well, you could be E or you could be Z, right? But you're always going to go via an anti-elimination. Okay. So, right, E product on top, Z product on the bottom here. Okay. Only that one hydrogen to pluck off, you'll form a mix of both. You can form either of them, but it's always going to be via an anti-elimination. So kind of keep that in mind. That's good practice when you're drawing your E2 mechanisms to show how that's occurring. What about for E1 reactions? If I'm thinking about something that's E1, I've got that carbocation intermediate, right? Right here. So electron density can move either way when I'm pulling off a hydrogen from my beta carbon. So in that situation, I don't have to worry about syn or anti, but I'm always going to form a mixture of E and Z because it can shift from either direction, but because E is more stable overall, that is your major product, just because it's a more stable alkene. Okay. And all of that information is summarized nicely here in table 9.6. We talked about stereochemical substitution reactions in the past. Okay. We just finished here with E1. You always get a mixture of E and Z, okay, with E predominating, and then everything for E2 summarized right here. Okay. So we take that information now and transition our thought briefly to cyclohexanes, and we'll finish this part 5 with our cyclohexane. How do these guys undergo elimination reactions? Well, let's start with E2. Okay, if I've got a 6-membered ring in that cyclohexane, if I'm doing an elimination, we have to have both groups in the axial position. Okay, and they have to be next to each other, right? The alpha carbon here and the beta carbon. And in order for them to be parallel and axial, they naturally end up anti to one another. Okay, you see that? Because there's no way for them to be parallel here and be syn, because that is not parallel, right? It's not an axial bond, it's an equatorial bond. So they have to both be axial in order for the two groups to be eliminated from a cyclohexane ring. So it doesn't actually happen all that readily in the most stable conformation of cyclohexane, because this is less stable. That's a bulkier group, so your halogen wants to be in an equatorial position. Which is not to say that it can't happen, right? It just has to happen via the less stable conformer right here. Right? This is the more stable with your leaving group in the equatorial position. You can ring flip it into an axial position, and then undergo your elimination and form your cyclohexene in this case. But the degrees of reactivity are just controlled by how readily something can adopt that less stable conformation. Okay, here it's possible to put a chlorine in an axial position. And these guys are always in equilibrium. It's less stable, but it is possible. If you start to put bulkier and bulkier groups there, then it's going to be less happy to adopt that axial position. Okay? And your reaction's not going to be very good in terms of the yield, okay? Which is all measured through equilibrium constants. Okay? Don't worry about the rate derivations, again, in the textbook. Right? Just think about the groups. Looking right here, for example, okay, this is a isopropyl group in an equatorial position. It's larger than the chlorine. It wants to stay here. So this is the more stable conformation with chlorine in the axial position. So it's pretty easy to do an elimination here because we want to keep those large groups in the equatorial position. That's something you could take advantage in synthesis. That's a fast reaction. Okay? Over here, this reaction's pretty poor, right? Because everything's in the equatorial position already. In order to ring flip and put everything in the axial position, that's really unfavorable. This arrow shouldn't even be that close. It's really going to favor this more stable conformation over here. That's going to be a poor reaction, really slow, really poor yields. But that's all for E2 eliminations where they have to both be in the axial position. E1s are easy. They're not concerted. They go through that carbocation intermediate. So if you have another alkyl group attached to that carbon and you could form a tertiary carbocation, then a piece of cake. You do that, go via E1, then you just have to pluck off a hydrogen from the axial position, and then you are in business. But notice chlorine wasn't axial to begin with. It was equatorial. No big deal. No ring flip necessary. Form the carbocation, pluck off your hydrogen, form your alkene. Okay. So keep that in mind, right? Stereochem is the biggest thing. And then briefly, if you've got a ring, right, know that they both have to be in the axial position in order to do an elimination. If it's E2, if it's E1, as we see here, just form your carbocation and move on with your day. Not too difficult. Big takeaways here, know E1 for sure. That's the biggest takeaway. Know how to predict for a tertiary alkyl halide if it's going to go via E1 or E2, and then know the stereochemistry from the back half of the video. Now for the rest of the chapter in parts 6 and 7, we'll see competition between substitution and elimination.